think the goal for today is very straightforward. I have two finals tomorrow. One in my security class and one in my operating systems class. So today, I am simply just going to look over a lot of the slides from, maybe even all of the slides from my security class. Yeah. This class was primarily like seminar based, and we gave lots of presentations in it and whatnot ourselves, so we only had lectures for like the first half of the course, so I think that's what our exam is over though. But yeah, I'm just gonna do this. I'm just gonna look at these slides and just write down general stuff that I think is interesting, because I'm not really even sure how to prepare for the exam itself. I don't really know what's on there. So who knows? But I did want to just take some time to look at the stuff regardless. Just as kind of like this is a refresher of anything. This is absolutely the first slide we ever saw, so. Yep, Enigma machine, the Turing bomb. World War II was a hotbed for this kind of activity. Cryptography. I think, what was it called? Was it called Blanchard Park? Gosh. I don't know. It was, I don't think Blanchard Park is correct. But it's the park in World War II where Turing built the bomb. Man. Where was it? Where did Turing create the Turing bomb? It's definitely not Blanchard Park. What is it called? Bletchley Park? Bletchley Park? Oh, hey, I actually was not too far off. Bletchley Park, an estate built in England, site of the United Kingdom's main code-breaking team during World War II. Yeah, that's pretty cool. So there's a lot of work going on here in World War II to combat the Germans. Very beautiful place, actually. Dilly knocks down Turing later, joined by other codebreakers and engineering staff. Yeah. Yeah, then of course you have the Enigma machine. Which was actually, I think it was made by, I think it was manufactured by people who were originally, this guy? Maybe not yet started. Yeah, I thought it was some guy. Man, what a small article for this. It's kind of surprising. Surprisingly small article. So yeah, World War II was pretty big for cryptography. Oh, Arthur Scherbius. Yeah, it's this guy. He was some like merchant. I don't even think he wasn't involved in the military at all in the beginning. He was probably some sort of engineer. Let's see, Arthur. I think. But this guy, Arthur Scherbius, his brother was in the military, and he was jealous of his brother because he was doing really well or something. Yeah, he's an electrical engineer. Electrical engineer. Invented the Enigma. His father, blah blah blah. This goes, this isn't very deep, but I can tell you, everything that I'm talking about right now, I know because of this book. Is it the code book I think it's called? This one, yeah. This book talks about it a lot. By Simon, whoever. Anyway. Steganography. So that's like when they would disguise plain text messages. Like, for example, writing a message on someone's bald head and then waiting for the hair to grow back. There wasn't like any sort of encryption on the messages, I don't think. Yeah, covered writing. Yeah, that's some early stuff. Cryptography, crypto's hidden, yeah. Oh, the Caesar cipher, so it's the Caesar shift. Alright, everyone knows about that. Shift 3 letter, yeah. Say just go 3 left. This is all pretty. Oh, Vigneri, I think that's how you say it. So this guy, he had like key. I think it was essentially a cipher shift or a Caesar shift, but he had like keys or something. Man, I actually don't remember. I'm a bit curious. Oh, check out this. I don't remember. It has some sort of key. I feel like this search engine sucks. I'm gonna say. Yeah, I feel like it sucks. Yeah, like, this is DuckDuckGo. This is better. Found it. Encrypting where each letter of the plain text is encoded with a different Caesar cipher. Increment is determined by the corresponding letter. Oh, really? Oh, the key. Yeah, so it has a key to determine the Caesar shift for each letter. That's a bit. It just adds another layer. Public key cryptography. RSA. Diffie-Hellman. My professor did some research with this e-voting, so he's always talking about it. Oh, the internet layered security protocols. I hate to say, but I don't think knowing the Caesar shift and the Turing bomb and Bletchley Park is going to help me on this exam very much, unfortunately. You know, it's always really confused me is freaking what the heck a checksum is. I ain't even gonna lie. Like, I get it's like a verification sort of thing, but how does it actually work? I actually think I was on the same exact page at the beginning of the semester asking this same question, and I obviously did not internalize it very well. Let's see, what does this guy LifeWire say? Checksum tells you if your version of file has been altered or not. Okay, that's just really it. So it doesn't, a checksum does not tell you whether or not it's authentic. It just tells you whether or not it's been modified. Okay. It's pretty interesting. But I still want to know how it works. I want to know actually how it works. Oh, it's a calculated value that represents the exact contents of a file or message. Okay. Oh. What? So it's just tied to a file. I wonder if I could get one. Can I get a checksum on something? That may sound pretty stupid, but I don't know. I'm gonna just try it. I could try to see if I can do it. Checksum file integrity, blah blah. Syntax. Oh, MD5 sum. That's currently it. Let's see. MD5 sum. Oh, compute and check MD5 message digest. Print or check MD5 128-bit checksums. Okay. That's pretty cool. So maybe I'm gonna do something. Let's go to this then. Let's go to... Okay. So let's say I want to do like... okay, and then we'll just put... I wonder what happens if I do MD5 sum on this, just empty. Okay. So that's the checksum, and then we can modify it and just put like 1. It's different, yeah. Now if I do it again, it should be the same. And if I change it again, 1, 1, it's different. Okay, so I just showed an example of what the checksum is. It's pretty cool. Yeah, but that would make sense that it doesn't tell you anything about who it came from. It just tells you if it was changed. Oh, Message Digest. Is that what? I guess that was what that said. Oh, I think the Vigneri cipher was an example of polyalphabetic, maybe. Monoalphabetic is like a Caesar shift, or it's just the same, I think. Substitution ciphers. The modular operation. Something that is interesting and still a bit confusing today. Matrix algebra. What is this? Kirchhoff's principle. I'm probably still that wrong. Kirk. This guy. Oh. That's interesting. Who's that guy? Whatever. Who's this guy? Dutch guy. A Dutch linguist. Kind of looks like Nietzsche. RSA is one of the big one. Oh, this stinking ass webcam is always falling over. Key generation, key distribution, blah blah blah. What the heck is that? Never heard of this. Is that a slime? Oh no, that's what this is though. I always wonder what that was. See, you know, here's a side on mathematical notation. That is a lot of the time, most of the battle with mathematical concepts is a situation like this, where like I look at this and I think, undefined? Like, oh, undefined, and that makes no sense. Now, this is referring to this. It's a function, and it's just conventionally notated in this way. I've encountered things like this in algorithms as well, and it seems like things like discrete math are full of little things like that. And that is a lot of the time most of the battle. So it's interesting. So in other words, if you find yourself not understanding something in math, you give yourself some grace, because it could just be some sort of notation thing. Man, this is confusing, I ain't gonna lie to you.
Imagine Alice and Bob want to communicate. Alice sends a message, "Hello," to Bob. However, there's no encryption involved, so anyone who intercepts the message can read it directly. Bob receives the message, but since it was sent openly, an eavesdropper could also read it without any effort. Now let's revisit the scenario with RSA encryption. Bob generates a pair of keys, a public key and a private key. Alice encrypts her message M using Bob's public key and send it. When Bob receives the ciphertext C, he uses his private key to decrypt it, recovering the
Yeah, this makes sense, but this is
original
obvious.
message. In this case, even if someone intercepts the encrypted message C, they cannot decrypt it without Bob's private key. Messages can be represented numerically by converting each character to its binary ASCII equivalent. For example, in the message "hello," each character can be written as an 8-bit binary. By
Okay. So that totally makes sense. He said, yeah. So we're seeing how the size of a character is 8 bits, and yeah, okay. I was just curious.
concatenating these binaries, the entire message forms a large binary sequence that can be interpreted as a single integer, which can be converted into a large decimal number representing. Concatenating these binaries, the entire message forms a large binary sequence that can be interpreted as a single integer, which can be converted into a large decimal number representing the entire message. Modular arithmetic is a system of
That's really interesting. I always wondered how that was done. I mean, it's pretty obvious, I guess, but
arithmetic for
I don't know,
integers,
I
where
don't think
numbers
about it.
wrap around when reaching.
Hold on, I'll be right back. Mountain Dew Baja Zero Sugar. Pretty good.
A certain value called the modulus. For instance, there are only 12 hours on the face of a clock. If the time now is 7 o'clock, 10 hours later will be 5 o'clock, and we do not say 17 o'clock. The key is, we are only interested in the remainder when a value is divided by 12. When we say A is congruent to R modulo n, it means that A and R leave the same remainder when divided by n. The phrase modulo n in parentheses applies to the entire equation. This is different from saying a mod n without parentheses, which refers to the result of the modulo operation itself. A mod n without parentheses gives a unique integer r such that r is between 0 and n.
Bro, what is he talking about? I like how he's explaining this, though.
Modular arithmetic is a system of arithmetic for integers, where numbers wrap around when reaching a certain value, called the modulus.
Oh, yeah.
For instance, there are only 12 hours on the face of a clock. If the time now is 7 o'clock, 10 hours later will be 5 o'clock, and we do not say 17 o'clock.
What is this? 2 times 12 plus 0. Yeah, that's 24.
The key is, we are only interested in the remainder when a value is divided by 12.
I don't understand what the hell is that supposed
When
to
we
show.
say A is congruent to R modulo n, it means that A and R leave the same remainder when divided by n. The phrase modulo n in parentheses.
Oh. So what that means is, yeah, A is congruent to R, and all of this is mod n, so this means it would be like the same remainder. You know, I have been confused by that. I've seen this mod n in parentheses on the right hand side of equations quite a bit, and hearing him explain that was actually pretty useful. So it just means the whole thing. As I'm saying, that's another there's another example with math. It's like, it looks so weird, but it's okay. So let's go write that down. You should never be too hard on yourself when it comes to math, because you just can't know what you don't know. So once you know it, it's not that bad, you know, honestly.
Applies to the entire equation. This is different from saying a mod n without parentheses, which refers to the result of the modulo operation itself. A mod n without parentheses gives a unique integer r such that r is between 0 and n, and r is congruent to a modulo n. The Euler's-Tauchant function, phi, is defined as the number of integers less than n that are coprime with n. In other words, it is the number of integers m such that the greatest common divisor, GCD, of n and m is 1. If n is the product of k distinct prime numbers, the Euler's-Tauchant function of n is the product of each of these primes minus 1. Euler's
This
and is
guy, what a
Euler.
nerd.
The Euler. If n is the product of k distinct prime numbers,
I don't really understand the -1 part, but
the Euler's Tochin function of n is the product of each of these primes minus 1.
yeah, why is that? I'm not sure.
Euler's theorem states that if m and n are coprime, then m raised to the power of phi of n, modulo n, equals 1.
Okay, I believe you.
The number 10 can be factored as the product of 2 and 5, where 2 and 5 are distinct primes. Phi of which means there are 4 integers less than 10.
Okay, this is a good example. This is a good concrete example right here.
Phi of 10 equals 4, which means there are 4 integers less than 10.
Wait a minute, wouldn't you say 1 minus 1 too? Is that dumb? Because it's also made up of 10 and 1, and 1 is 1 prime? Oh my gosh. I don't know. Mathematics is not my strong suit. No, wait. Because it only... what? Oh, it's greater than 1, okay. So then this makes sense. So 5 and 2. But wait, 2? I'm so dumb. Like, what? Oh, 2 is the only even prime number. That's pretty cool. So yeah, let's do 10. So yeah, 10 is factorized as it's 5, 2. Okay. So 5, 1, 2, 1, which is 4, 1. That's 4. Okay, I agree with this right now.
Factored as the product of 2 and 5, where 2 and 5 are distinct primes. Phi of 10 equals 4, which means there are 4 integers less than 10 that are coprime with 10.
Yeah, so this means 4 integers. Isn't it less than or equal to, though? From this definition. Positive units, yeah, less than or equal to 10. That are... what?
1, which means there are 4 integers less than 10 that are coprime with 10. 1, 3, 7, and 9. The factorization problem is a core concept in cryptography. The problem is based on the fact that, given 2 large prime numbers, p and q, it is easy to multiply.
Wait. How is it coprime? Oh wait, is it because the only shared factors are 1? Is that what it is? The GCD pair, no con other than 1. Yes, which makes sense. 1379. The only. Yeah. Okay. So yeah, coprime. Pairs of integers have no common positive factors other than 1. So, yeah. That's interesting.
Multiply them together to get their product n. However, given only n, it is extremely difficult to factor it back into its original primes p and q, especially when p and q are together to get their product n. Two large 4 equals 4, which means there are 4 integers less than 10 that are coprime with 10. 1.
The frick is this? 1 to the 5. Why is it doing stuff to the 5? Oh, that's interesting. He's like making them here. That's so weird.
3, 7, and 9. The factorization problem is a core concept in cryptography.
Yes, it is. I know this. Okay, this is what I do know.
The problem is based on the fact that, given 2 large prime numbers, p and q, it is easy to multiply them together to get their product n. However, given only n, it is extremely difficult to factor it back into its original primes p and q, especially...
Look at this. Okay, this is good. This is what I've actually taken away from classes. Something that has been explored a lot, and something that is actually very interesting to think about, because it seems like, I don't know, but it's because of the modular operation, I think. But yeah, this is what so much of it is based off of, is this.
When p and q are very large. Now, let's move to the RSA encryption algorithm. The first step is key generation. Select 2 large distinct prime numbers, p and q.
Okay, got it.
Multiply p and q to
Get
obtain
in.
n. N is used as the modulus. Calculate phi of n, which is p minus
Okay.
1 times q minus 1.
Ooh. Yeah, which is up here. Yeah, the function, the Totian function. P minus 1 times Q minus 1. Okay. That's
Choose
easy.
the public exponent e, coprime with phi of n.
Choose E, coprime with 5 n. Okay. Okay, I'll actually just write down the steps after this.
Compute the private exponent d, the modular multiplicative inverse of e modulo phi of n, and it can be computed using the extended Euclidean algorithm, and it verifies the equation e times d equals k times a phi of n plus 1. The public key is the pair n and e. This key is shared publicly and used for encryption. The private key is d. This key is kept secret and used for decryption. Now let's move to the encryption step. First, we need to convert our message hello into an integer m. Then, we use the public key n and e to encrypt the integer m. The ciphertext C is equal to m raised to the power of e modulo n. Now, let's move to the decryption process. First, we use the private key d to decrypt the ciphertext C to recover the message m. The message m is equal to c raised to the power of d modulo n. Since c equals m raised to the power of e modulo n from the encryption step, substituting this into the decryption equation, we get c raised to the power of d modulo n equals m raised to the power of e times d modulo n, and we have e times d is equal to k times p of n plus 1.
This is
Then
AI
we use
voiceover.
Euler's
When was
theorem to
this?
simplify.
Oh, could very possibly be AI voiceover. Send Python script, please. That's funny.
Simplify the equation to m. Now, let's move to an example of RSA encryption in action.
Okay, let's do it.
Alice wants to send the message hello to Bob. She first converts it into an integer m. Then, she uses Bob's public key n and e to calculate the ciphertext c, where c equals m raised to the power of e modulo n. After that, she sends the ciphertext to Bob. Bob receives the ciphertext and uses his private key D to decrypt it, where m equals c raised to the power of d modulo n. If Eve intercepts the message, she cannot decrypt it because she doesn't have Bob's private key.
Is that it, bro? That is it. That's literally it.
I have to kind of apologize. I
What is
thought about
this?
how to do this, right? I could have done this with actual how the RSA system would actually work, with actual numbers.
Who's this
with
guy?
Actual, like, long message and all that kind of thing. And we could do it with computers. I could show you how to do it. But I thought, no, I actually want you to see the maths of what's going on. So I've picked simple things, like a one-letter message, okay? So forgive me for that. Anish.
Does that say we went back?
Okay. This guy seems like a good teacher, though, to be honest. Just, it's got the beginning. Did you see the beginning yoga posters?
I have to kind of apologize.
Beginning yoga. Maybe it's like a high school class. 29 October 2014, before ChatGPT, guys. Before ChatGPT, when people just learn stuff with their head. Maybe, actually, maybe that's not even true. Okay, so let's just outline the steps. I had the general steps here. Yeah, so it's like so the first one is key generation. And we saw yeah. Just to press P and Q. And then, yeah. Put in NP times Q. Then you find the, how do you say that guy's name? How do you say it? It's like Euler? I don't know. Euler? I don't know. People just say whatever they want. Let's see what he said. Let's just see how they pronounce his name. Man, that's a cool piece of paper. Okay, bro. What the heck? Can you just say his name once? Dude, for real? This guy's being weird.
On top. Are coprime. Then m raised to the power. Here's totient function. The Euler's totient function.
Euler. I don't know. This seems like AI though. Whatever. I'm just gonna pronounce it Euler. Okay. So after that, you will find the Euler's totient function. Euler's totient function of n, which seems to be p minus 1 times q minus 1? That shakes out.
That are coprime with 10. 1 is used as the modulus. Calculate phi of n, which is p minus 1
Yeah, there we go. Compute this.
times q minus 1. Choose the
Choose E. Yeah, what is EC such that? I think such that can be like just a colon. E such that is 1 is less than E, which is less than this function. Is that phi maybe? And the GCD of E phi n is 1. So you just gotta find that.
public exponent e. Coprime with phi of n. Compute the
Oh, prime. So it just means coprime. In other words, yeah. E is coprime with 5n.
private exponent d.
Now you have to compute the D, which is D is for the private key. Compute E, compute D, which is okay. Compute the private key D such that D is congruent with E to the minus 1 mod phi n, which is equivalent to E times D equals K times phi n plus 1. What?
The modular multiplicative inverse of e modulo phi of n. And it can be computed using the extended Euclidean algorithm.
What is that? Extended Euclidean algorithm. Compute man, all these math things, man. Yeah, ax plus by is that what it is? Nope. Whatever.
And it verifies the equation E times D equals K times a phi of n plus
What the
1.
hell is K?
The public key is the pair n and e. This key is shared publicly and used for encryption. The private key is D. This key is kept secret and used for decryption. Now let's move to the encryption step. First, we need to convert our message hello.
That's really it. The key generation is actually the hardest part for me. The encryption decryption is very easy. It's just literally functions, whatever. Alright, that's good. Yeah, that was... Oops. Yeah, what is the difference between Diffie-Hellman and RSA?
Illegal users.
Oh. Diffie-Hellman uses the same key, so you have to send the key, right? Diffie-Hellman is primarily used for communicating. Oh. Interesting. I see. So they are actually kind of different. I had thought that they were pretty damn near the same. Headphones. That's interesting. Well, let's just look up Diffie-Hellman then. Okay, yeah. So yeah. Hold on, bear with me. key exchange. Okay. Is this discrete logarithm problem? Oh, here it is. Yeah, based on discrete logarithm problem, suppose P prime and G a generator of Z. You know what? That's we may as well iron that out right now too, because I don't know what that is. And I that's this. I don't know what that is. Generators, I don't know what that is. Serious? Is that really it? I've seen this generator term throughout the semester as well. So what, is it a set of numbers? I don't understand that. This is very interesting. So G is a number. Holy crap. Whoa. So it's also called a primitive root. Check this out. This is what Gemini gave me.
So G is a generator of the set. Oh my gosh, sorry, this is fucking mowing outside. Whatever. So G is a generator of this. Of this, which is the set pretty much 1 to p minus 1. Sorry, should I hit it, right?
What is a quadratic residue? Math is so crazy. And you know what I'm learning? Maybe I'm a bit late to the party on this, but a computer science degree is just a math degree. was some more interesting stuff sprinkled in there. And if it was just pure math, that would be so boring. But it's kind of nice because you get all of the really cool, interesting, deep parts of math. And then you get to do some programming too. It's kind of a nice mix, you know. Sometimes it is. This semester for me has been so math heavy. And programming stuff has been kind of on the side. Oh yeah. I remember learning about this.
forget what this was super relevant for. It's something we did in homework. Yes, that's what it is. It allows computations to be performed on encrypted data without first having tried it. That's one. What's this? What if I'm gonna change the music. We're gonna go to some Jungle Wizards. Also, I'm gonna change some stuff around here. You know, I used to think that there was like a sort of time limit on how long you could sit down and like study or something. And I thought it was like an hour. I was like, oh, after an hour you're cooked. And I'm thinking, like, how does that even really make sense? I mean, is there a limit on how long I can sit and play games? No, you wanna know what the limit is? When I get tired. Or when I'm done playing it. So, like, it's kind of the same thing with really anything. I mean, there's no time. I think we kind of say that just because we don't want to sit down and do anything like that, you know? Understandably, because a lot of them sucks, but I don't really think it is, you know, extremely meaningful. Like to put like a limit on yourself. Okay, so identity-based crypto system. Yes, I don't remember this one. It's by the same guy from RSA. I know, I get up all the freaking time. I don't even care, man. I don't care. Say what you will about it. I get up every 2 seconds. I don't care. So what is this identity based? I mean, obviously, we didn't really learn about this very much, which makes me believe that it's not too crazy or too important. This doesn't seem very important. I don't remember it. And whatever. Shamir, 1984. Book I've never read. They're really cooking up cryptographic schemes though. Like after the late 20th century, they're like, let's just do everything. Let's just encrypt everything. so it's literally a scheme based on a well pairing. I don't know what the hell that is. What is this? Hey, you know what I should do? I should take this. Do I have another? I could take that here. And do this because I'm tired of backing out of this. Zero knowledge proof. We definitely were talking about these ones. That's pretty easy. Let's try to do a Hamiltonian cycle real quick. Vertex 1, 2, wait, actually I can do circles. 1, 2, 3, 4, 5, 6. Let's put this one in there. Yeah, okay. So how can we do it? This is actually really easy. So this is the starting. So we start here, and we need to end here. So a Hamiltonian cycle would just be, I guess there's actually a few different ways. So we go like boom, 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 boom. Easy. Or we could go like boom, boom. Actually, boom, 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 boom. I think you could do anything, right? I mean, can't you just pretty much do anything per se? These are all cycles, whatever. That's interesting though, that's cool. But for a large graph, okay, that's probably pretty interesting. Yeah, zero knowledge proof. We learned about these thingies. challenge response, not interactive, yeah. We did need an homework. I definitely got some help on that. Let me just tell you that right now. I got some help on it. See commitment slides. Where are those at, bro? What do you mean commitment slides? No control F. Okay, interesting. Wait, are these it? I think this is, yeah, this is overview. Okay. So they'll be coming up. Luggage transfer.
this is getting pretty boring. I think I might be getting done with this class. It's like, there's only so much I can do at this point. I don't even know what's on the exam. It's crazy. Alright, yep, 2 hours is pretty good. I think I'll hop out of here and get some lunch, so. Alright, see ya.